Welcome to today's webinar. We'll be talking about Wolfram language functions, the basics of function structure. So this is going to be a very simple webinar. We'll just cover some basics about functions, which are a fundamental part of Wolfram language, or of any programming language for that matter. Um, we have a lot of material, but I'm not going to go through all of it because this is meant to be an online course, which takes much longer than the time we have now. So in terms of time, I think this webinar will take about 1 hour, hour and a half. And we'll just cover, I'll try to cover the things that most people are going to be using most of the time, just in the interest of this webinar being useful. If you are interested, you can do a deep dive yourself with the notebook materials by yourself. But in terms of the live webinar, we'll be covering the most basic things, so to speak. But I still hope that even if you are somewhat experienced in Wolfram language, I think you'll still find some things useful in the webinar, even though there will probably be some overlap with your existing knowledge. So yeah, for the next 1 hour, hour and a half, we'll do that. So sit back and enjoy, or if you prefer to follow along with the code, you can access the notebook. As Chris was mentioning, you can access the notebook via the link that is in the chat if you're watching on YouTube, or above the chat if you're watching us on Big Marker. So with all of that said, let's get into it. What are we going to be learning today? What are the learning objectives? The main idea is for you to kind of get an idea of what makes a function good, or if you prefer the inverse, what makes a function bad. So to achieve that, we'll start with the basic function structure. We'll learn about pure functions. We'll see what the difference is between a normal named function and a pure function. It says it's optional here, but in my opinion, pure functions are very useful, so we'll definitely cover that. Then we'll dive a bit deeper into kind of the structure of each function. We'll talk about arguments. How do we add arguments? What is the value of adding arguments? Then we'll talk quite a bit about restricting arguments. So how do we make sure that the arguments are basically what we want them to be? And then we'll kind of we'll look at some useful tips that will help you write good functions, readable functions, high-performing functions, and so on. So that's kind of the little plan that we have for today. So let's get right into it. So I mentioned that the main idea of today's webinar is to learn what makes a function good. And that partly depends actually on who you are, in terms of if you are a professional developer writing a product, a good function for you will mean probably a different thing than if you're a hobbyist just writing personal projects. But even with that, there are some principles which apply to all functions, and we'll try to cover the kind of the main things that you should keep in mind when you're writing your functions. Just see a question in the chat if I could increase the font size, and I will. So apologies for that. Hopefully this is a bit more. Hopefully this is a bit better. So generally speaking, what makes a function good? A few elements here. One is your function is robust to all input. In other words, it is difficult to break. So, and if it does break, it gives you kind of a descriptive error message, or it gives you some indication as to why it's broken and what you have done wrong and how to fix it. Another criteria is it gives a clear output. So this is not just about errors, but if your function is meant to be adding up two numbers, to take a simple example, then the output should be the sum of those numbers. Fairly obvious. The function is flexible, so it has the potential to be applied in contexts beyond its original scope. So this criteria is a bit more abstract, but the main idea behind this is that typically when we write a function, we have an idea in mind of what it's going to be used for. And a good function typically can be used for things that are close to what your original intention is, but still in the same vein. It's a bit difficult to explain in abstract, but you'll see what we mean by that when we get into the examples. And then finally, has clear documentation. So the function can be used and understood by others. And that criteria, especially the last one, is very often overlooked, unfortunately. Um, so when people write functions, and this applies even if you're, because obviously if you're a professional developer and you're writing functions that are going to be used by other developers, then clear documentation is critical. But I would say even if you're working on a personal project and you know that nobody else in the world is going to see your functions, I would argue that clear documentation is still very important. And that's simply because when you write the function now, you obviously have an idea of what it does and you have an idea of what it works. But then you look at it 2 months later, and if your function is not clearly defined and documented, then it becomes a problem for yourself. So I would say it's almost always worth the extra time to bring some clarity into your functions. So to kind of summarize those points, when presented with a well-designed function, you should be able to read and understand its documentation, apply it in a variety of contexts, and receive the results you expect. So basically, you should know what it does, and it should give you what you expect it to give you. These are just guidelines, of course. Sometimes it's useful for a function to be deliberately inflexible with few or no options. I think a good example of functions like that are deliberately inflexible is what we call predicate functions in Wolfram language. So functions that end in Q. So things like string Q, string contains Q, integer Q, and things like that. They're very, you could think of them as very simple functions that take one argument. Usually, typically they take only one argument and they return true or false. So if you use string q, you pass it a string and it tells you, or you pass it any object and the function returns true if the object is a string and it returns false if it is not. So that's a very kind of simple function. It's not very flexible, but that is the intention behind it. So just to kind of visualize the simplicity of predicate functions, this is, so we're looking at two bar charts here. The left one is for all the Q functions, for all the predicate functions, how many numbers of argument they take. And you can see that the majority of Q functions take only one argument. And then we'll talk about options as well. So if you're not sure what options are and how they're different from arguments, that's fine. We'll cover that a bit later in the webinar. But the important thing to see here is that most Q functions take 0 options. There are some that take 1 or 2, but it's very rare. And in fact, I wonder which Q function takes 7 options. That'll be interesting to find out. But in any case, most of them take 0. Okay, so let's talk about the structure of a function. So let's move from kind of the abstract discussion of what makes a function good to the actual programming and syntax of it to see how we can kind of define our own function. So what we have here is an example. You can think of it as the anatomy of a structure. So this is how you define a function in Wolfram language, and the callout labels you see on the graphs tell you what each part is. So you can see for this function, function name is the name of the function. Then in square brackets, we have the arguments of the function. And then the last element in the square brackets, if it exists, is the options pattern. Then we have this special syntax here, which is colon equals, which is different from how you define a variable. And colon equals is shorthand for set delayed. That means that whatever goes on the right-hand side of the function is not evaluated immediately. Instead, its definition is stored, and then it is evaluated when you call the function later on. And everything on the right-hand side of set delayed is essentially what your function is going to do. And typically what your function is going to do is it's going to take the arguments that are passed into the function, and it's going to perform some operations on them, and then it's going to return a different result. So some common practices common practices slash conventions. Again, um, important if you're collaborating with other people. Uh, it's important to have kind of shared expectations of things like what does a function name look like, just so anyone can see at a glance, even before they inspect the actual body of the function. Um, they can see at a glance that they're looking at a function. So for readability, we typically use lower camel case, where the first word starts with a lowercase letter, then each subsequent word starts with uppercase letter. Very common convention for functions, for function names, I should say. And then we use upper camel case um, for symbols for any options. So if you have any options that go into your function, um, you would name them. You can name them anything you want. Um, but typically we name them with this convention, upper camel case convention. Um, a few more things to mention about function names. In Wolfram language, function names can take any any Unicode characters. So you could have a function name like this one, which is fairly simple, just Latin letters. You could have a function name that is made entirely of emojis if you want. Um, Wolfram language is not going to stop you from naming your function however you want. However, for practical reasons, it's usually it's usually very easy to stick to Latin characters, just because if you're once you define a function, presumably you're going to be using it later on in your code, so it's much easier to type out if it has a easy name rather than something like emojis. But in terms of acceptable characters, I'm pretty sure any Unicode characters are acceptable in function names and in argument names and in option names. A few other conventions in terms of naming of functions. So if your function is always going to evaluate to true or false, we use name q. So if you have a function that checks whether a number is even, you can call it even q, and then it will take one argument, which is the number, and then it will return true or false. And in fact, we do have this function built in. And as I mentioned previously, we'll call these functions predicate functions, and they're pretty much the most simple functions you will find in Wolfram language, but they are very useful. For numerical functions, you can use capital N followed by the function's name. So for example, nsolve. And if you're referring to global variables in your environment, you use $sign. So we have a lot of $sign variables already built into Wolfram language. So something like processor count is the first one that comes to mind, which will look at how many cores your CPU has. You can, of course, write your own $sign functions, which check for something else. And if your function is looking into system slash global slash session variables, a common convention is to use a $sign to kind of preface that function. Okay, quick example. So we have discussed the structure of functions. So let's actually write one. So we start with clearing the definition of a function. And just 1 second, because something's wrong with my keyboard. There we go. So in many cases, we start by clearing the definitions of a function, especially if we are, well, in the context like this, where I'm looking at a long notebook where I'll be using a lot of example functions and maybe I'm repeating the names. It's always a good idea to clear previous definitions, just so you can know that whatever comes after it is the only definition of your function. If you're using similar names for functions, sometimes you can overload functions unintentionally. And overloading is something we'll discuss in this webinar, actually. Overloading can be very useful, but if you do it unintentionally, you might be wondering why your code is behaving unexpectedly. So always a good practice to clear all before you start defining your functions. So here we have a fairly simple function we call multiply by 3, which is the name of the function. And in the square brackets, we have the arguments. So in this case, our function has one argument, which is called num. And then this underscore here that you see at the end of this argument, and at the end of each argument actually stands for any Wolfram language expression. So we'll get more into this when we talk about filtering our arguments and things like that. That's when the underscore will become more relevant, more useful. But for now, you can kind of memorize it as a normal function notation, that the argument names are have underscore following them. Okay, so we have our name, the name of the function. We have the arguments of the function. We have set delayed, and on the right hand side we have what our function actually does. So in this case, it just takes the argument that is passed into it and it multiplies it by 3. So you can see obviously a very simple toy function, but you can see some of the principles we talked about already. So the function has a very descriptive name. The name is exactly what the function does, multiply by 3. It takes one argument. Again, the argument name is very clear as well. It expects a number. And then the actual the functionality is fairly simple as well. So let's define that and let's add some options. So the way to add options to your functions is calling this options function, excuse me. And then you pass in the name of your function and then you define the options. So here we have an option to take the modulus of the result. And then we can test our function by passing it some arguments. So if we call it without any options, we just pass it a number. It just multiplies it by 3. So here we pass 7, we get 21. And then when we pass it by the modulus, we get the modulus as a result. So in most kind of the most simple terms, this is all that a function is. And this is essentially what is happening when you're using any Wolfram language function that is already built into the language. So here we're talking about defining our own functions. But obviously in Wolfram language, we have thousands of functions that are already defined for you. And obviously they are more complicated than this one, than the one that we are looking at. But the principles that go in creating them are the same. So the idea is that even though we have thousands of functions, obviously in programming we always need to do very kind of things that are very unique to our workflows. So even though in a lot of cases you will find that functions already exist for what you're trying to do, in many more cases you'll find that you need to write your own. But there is no fundamental distinction between built-in functions and functions that are written by you, other than the fact that the built-in ones are very highly optimized. Obviously, we have a team of programmers that spend a lot of time into making sure that the functions are robust, clearly documented, readable, flexible, and so on. But if you write a very good function yourself, then it is basically equivalent to a built-in functions. Okay, so let's talk about pure functions now. So what we saw in the previous section is we define a function, we always give it a name. So if I deleted this name, this wouldn't be a valid function. This is not a real thing. So a function, when you define it like this, a function always needs to have a name. And the value of that is that once you define a function, you can call it multiple times later on in your code. But what if you want to do something much quicker? What if you want some functionality, but you don't really want to assign it to a name? You don't want to do that set delayed. You want to avoid all of the details of the syntax. You just want the pure functionality, so to speak. And this is why they're called pure functions. In other languages, they may be called anonymous functions or lambda functions. It's all referring roughly to the same thing, which is you just want the pure functionality without all the syntax or the details that go into it. So in that case, you use pure functions. And I'm not really sure why pure functions are optional in this webinar. In my opinion, they're probably, well, again, it's highly dependent on what you do, but they are at least as common as normal named functions. So we'll look at them in some detail in this webinar. So the benefit of pure functions is it's defined in the same place it is used. meaning that somebody reading your code will not have to go hunting for a definition. I would say that's another benefit other than the things that I mentioned. But yeah, so if somebody is looking at your code and they see that, well, if they see multiply by 3, they can kind of guess what the function is doing. But if you have a function that does something slightly more complicated, just looking at the name is not going to be enough to know exactly what the function is doing. But if you have a pure function where everything, all the functionality is already in the syntax, then it's much easier to read. So that's one benefit of pure functions. Um, Typically, you use pure functions when you want to do something very simple. So, for example, multiply by 3 is actually a good example because you don't need to, i- i- it's a fairly simple arithmetic exercise. So, you don't really need to create a whole function for it. You can just write a pure function for it. Another very common use for pure functions is when you're only using them once. So, as I mentioned, in the named functions, one of the main benefits of having a name and storing the function in that name is so that you can reuse it later in your code. But if you know that you only need to do something once, that's when a pure function can help you. And you can also use them as part of a larger function. Again, that's very useful. I would just be careful about readability when you have a lot of functions, especially when you're mixing named functions and pure functions. Your code could become difficult to read, not necessarily, but it is something to keep in mind. But yeah, that's when, again, that's when pure functions could be um, useful. So let's look at what pure functions look like and how do we actually define them. So in terms of syntax, we have a few options in defining pure functions. Technically speaking, all pure functions use this function under the hood, but you don't necessarily need to write it. If you want the formal syntax of a pure function, this is what it looks like. So you have function and you have square brackets. Um, you have parameters followed by the body, and the body is just what your function does, essentially. So you can see some examples here. Let's define this function. Um, This is our pure function, what I have highlighted on the screen. So you can see we start with function. The first thing is the parameters. So the arguments, the parameters, it means the same thing in this case. Um, and we say that our pure function is going to take one argument, which is going to be called n. And then the second element in the square brackets is what the function is actually going to do. And in this case, it's just going to square the n argument. And then after that, we pass it the actual argument. So we can we can see the result, and in this case we're passing it x, and as we expect, we're getting x squared. So if you were to write that in a normal function, you would do something like this: square argument, for example. You would say that you want n, and then you would define this, and then once you call it, you will get the same result. But as you can see, this is a much more verbose way of doing it. And since we are doing something very simple, which is squaring an argument, we might just want to do it like this because it's much simpler. But functionally, both of those are accomplishing the same thing. It's just that with a pure function, it's much quicker and easier. Um, Here is another pure function um, with a few arguments, and here the arguments are p and q, and they're being summed. So we pass it x and y, and they're being summed as we would expect. Nothing very interesting happening here. Instead of naming your arguments, as you can see, so far we have always given our arguments some names. In the previous slide, it was num. In the pure functions, it's n, but we don't necessarily need to give them names. We can just use this slot notation, which is a special notation specifically for pure functions, and we can say that this is a slot for any argument. So in this pure function, since we only have one argument, we can denote it with this slot, and then any argument we pass goes into this slot. So we don't need to think about names. And typically, if you're looking at other people's code, you will find that pure functions are, I would say, almost always use this slot notation. But again, functionally, it's doing the same thing as if this argument was named. So essentially, this is the same as this. It's just that with the slot one, it's again, it reduces the kind of the length and the verbosity of your function. Okay, so this is how you define pure functions using this function symbol. But there is an even shorter way to do it, and it is by having your pure function followed by an ampersand. Again, in reading other people's code, you'll find this notation very often. These parentheses that you see here are not mandatory, so you could very well have a function that looks like this, and this is just as fine as this. Again, functionally, they are doing the same thing. Where you would use the parentheses. So the parentheses, if you don't need them and you include them, there's no harm done. So your code is not going to be functionally different. But in some cases, and I think we actually have an example of this here, maybe later on, I believe in some cases where you have a more complicated piece of code and your pure function is intended to only be a part of that code, it's very useful to put parentheses around the pure function itself so that the ampersand knows the scope that it is applying to. So we do have an example of that later on. It will be more clear when I show you the example. But in terms of a pure function, this is the shortest possible way you could write a pure function. So you can see that, so here we're using the slot notation. We're squaring whatever goes into the slot. And the ampersand just means this is a pure function. And this is just the argument we're passing to it. So you can see already how much shorter that is compared to this way of writing the same thing. Not only does this go on multiple lines, but each line is much longer than this. So this is the main reason people use pure functions. It's just much, much quicker to get especially simple things done. And in terms of pure functions are just as powerful as named functions. So it's always very tempting, especially when you're working on a project, you're exploring ideas, you want to try different things, you're not really sure what works yet. You just write a quick pure function to test something, and then you kind of leave it in your code and you move on with your life. So you'll see pure functions littered everywhere. That's why I think it's an important part of the webinar to talk about pure functions because one, they're very useful to you as a developer, and two, if you're reading other people's code, you'll see them everywhere because it's useful for other people as well. So we talked about the slot notation. So when we have a single argument, that's it's fairly clear what the slot does. The slot just takes the argument. That's it. If you have multiple arguments, you can specify which one goes in which slot. So, for example, you can see here we have slot 1, which means take the first argument. Now, in this function, there's only one argument. So this is the same as just not having the slot at all. But if you have multiple arguments, that's where numbered slots become more useful. So here you can see we have a pure function, which is this, the highlighted part. And then we're passing it 3 different arguments. And we only want the function, we only want our pure function to do something with the second argument, for example. That's where we kind of number our slot and we say square the second argument. And you can see the second argument here is y, so we get y squared. And you can obviously combine, for example, you can do this and so on. You can essentially refer to the arguments again without the arguments being explicitly named. You're just relying on the order with which they're being passed to your pure function. Another useful thing, if you're dealing with associations specifically, you can refer to the keys in the association. So if I want to, so this is the association that I want to do something with, and I know that I want to do something with the value of the key b, which the value is y. So I can just refer to the key with its name in the slot, and that's going to extract the correct value out of my association. Um, so in this case, yes, we're referencing b. The value for b is y. So this is what gets slotted into this notation here, and then it gets squared. So there are a few other things, but I think that pretty much covers the basics of pure functions. But let's go through them quickly anyway. Pure functions can be used as arguments for other functions, and this is where I was talking about um, kind of mixing and matching named functions and pure functions. You can, again, Wolfram language is not going to stop you from doing that, but you can see immediately this becomes more difficult to read as a function, um, because we have a named function and we have arguments which are derived from a pure function which takes arguments which are defined at the end of the line. So even with this very simple example, you can see that our function becomes immediately um, less readable once we start mixing types of functions together. But again, it is possible, and if you feel like this could be useful for your workflow, then by all means, um, go for it. It is a possibility. So additional slot notation. There are a lot of things you could do with slots specifically. So if you have a double slot, or what is called technically a slot sequence, that refers to all the arguments. Um, Double slot or slot sequence and a number, slot sequence and n refers to the nth argument and all the arguments after it. So if we have f slot sequence 2, it is essentially doing something like this. If you're used to slicing lists and things like that, this is the pure function equivalent of this syntax. So it takes everything, so it takes the second argument and everything that comes after the second argument. All of these, by the way, they're useful to know, but they are not very common, so you won't find yourself using them very much. But um, I just want to put them in your mind just in case you ever find yourself in a situation where you need to do that specific thing. Maybe you remember, oh, there's a notation for that. Let me look it up. I don't expect you to really remember all of that by heart. Um, and probably the most rare one is a pure function that references itself, which takes slot 0. I haven't really found a compelling use case for that, for this specific notation, but there it is. It exists. Um, Precedence. So when code is evaluated, operators are applied sequentially according to their precedence. So you can think of this as an extension to mathematical precedence, where multiplication is applied before addition and so on. So if you have this expression here, the multiplication happens first, and then you get the addition. Oh, this is the example that I was looking forward to, which shows you the kind of the value of using parentheses. So here we have two lines of code that look roughly the same. It's just that with one of them, the actual pure function is defined in parentheses, whereas with the other one, we're just using the normal ampersand. And you can see that we actually get different results. Just to kind of explain quickly what the function actually is supposed to do, we're passing it a list of numbers and we're applying oddq, which is one of the predicate functions that I mentioned earlier. And oddq checks whether the argument is an odd number. So we're saying only give me from this list that we're passing 1 to 5, give me the numbers that are odd. So obviously the expected result is 135, but you can see that with the first line that we have here, we're not getting the expected result. And that's because the ampersand, which is what defines a pure function, gets applied to the whole expression rather than just the predicate function. So you can see that once we kind of set the scope right by wrapping our pure function in parentheses, we get the right result. And the way you can inspect that, by the way, and this is, I mean, this is true for pure functions, but it's also true for any Wolfram language expression, especially if you are especially if you are using a lot of shorthand notations and things like that, is to wrap your function in this full form function, which gives you kind of the most formal definition of your function. So you can see that even though these two look fairly similar, almost identical, having the parentheses to instruct your ampersand um, as for what it is being applied to can make quite a bit of a difference. So just before I move on to the next slide, there's a question in the chat by Trevor Martin saying, could I use slot notation instead of okay, so Trevor has some code and he's asking whether he could use a slot notation. So I'll just copy and paste the code in the notebook. I hope you don't mind that, Trevor. It looks um, fairly innocuous. So Trevor's asking, could I use a slot notation instead of? I see you're already using a slot notation. Oh, but can I use a slot notation instead of function x greater than 2? So you're asking if you could use a slot notation here. You could. So let me just see what the function does. Let me see if I can do this live. You could absolutely use a slot notation instead of your x. And I think the way to do it would just be this, if I'm not mistaken. That seems about right. Let me just copy and paste it again to make sure it's giving us the same output. Yeah, that seems right. So you can replace your x's just with a simple slot, and that will do the trick. Hopefully that answers your question. Stefano is asking, the parentheses close after or before the ampersand? You close the parentheses after the ampersand, as you can see here. Okay, so moving on to arguments. We already talked about arguments, so well, arguments are not necessary for a function. A function can do something without taking any arguments. Typically, you will find one or several arguments in your functions. So let's talk first about implementing the arguments, how we can define them, and then we'll talk about things like restricting arguments, and we'll talk about why that is useful. So as I mentioned, in terms of naming conventions, we can use lower camel case for arguments. So let's clear the previous definitions of this. And again, we're defining, now we're back to named functions. So we're defining a function whose name is random real. We're taking two arguments, lower bound, upper bound. And on the right-hand side, we are generating a random real number that has a lower bound that is this, the first argument, and upper bound, which is second argument. And we're generating one number. So let's define this and let's test it with some bounds here. Oh, let's actually test it random real, and we can pass, let's say 1 to 5, and then we get a number. We get a negative number because we are getting the negative of the lower bound here in the actual body of the function. Got me confused for a second. As I mentioned, a function doesn't need to take arguments. So typically when you have a function that you just want to store some action inside a named variable, so to speak, you can use this notation. So you have your name of the function and you just have empty square brackets. On the right hand side, you just do anything you want to do. And then you can call that just like a normal function, except obviously you don't pass any arguments. And that should work. I wonder why it doesn't. Oh, yeah. So you call it like a normal function, you just don't pass any arguments. And that should work as well. Let's move on. Okay, restricting arguments. So this is where we start getting into kind of the argument parsing and making sure that what goes into your function is what you expect to go in your function. So yeah, actually, this is a good example. So let's say we have a simple function here which takes a string and it takes a string and it makes it uppercase. So in that case, you want to make sure that whatever goes into your function is a string, because to uppercase only applies to string. So if you call, let's say you call to uppercase and you call it with a number, it doesn't really make any sense. You can't really uppercase a number. So how do you make sure that when you define your function, how do you say I only want this function to work with strings and nothing else? Well, there are a few, actually, there are a lot of ways you can accomplish that, but the most straightforward is by what we call restricting by head. So that begs the question, what is head? And a head, you can think of heads in Wolfram language as, roughly speaking, as types. So we talk about strings, we talk about integers, we talk about real numbers, and so on. Um, so the simplest way you can accomplish this is by checking whether the type of the argument is a string. And every symbol, every expression, every argument in Wolfram language has a head that you can check by applying the head functions to it. So if we apply it to a piece of string, we get string. If we apply it to a number, we get integer. If we apply it to a decimal number, we get real, and so on. So there are a lot of different heads, and the simplest way you can restrict the arguments in your function is by specifying which head you expect this argument to be. So the way to do it in terms of syntax and notation is after the underscore, you just specify the head. So here it's probably less clear because we have the argument is named string and the head of the argument is also string. So we can change the name of the argument to something else just to make clear which is which. And it should work the same. So we are saying we have this to uppercase function and we have one argument, which is called text now. And we are saying that this argument must have a head of string. And then we test it. So we pass it something that is a string, and we can see that it makes it uppercase. And then we pass it something that is not a string. And this, again, not text is not exactly accurate because it is text, it's just not a string, strictly speaking. So let's call it not string. And then when we pass it something that is not a string, so something that doesn't match this this restriction, we just get a definition which is itself. So basically, this is the Wolfram language way of telling you that the function that you are asking for doesn't exist. So the best way you can define this expression is by itself. And so it's not the case that this not string symbol got put into the function and then this gave an error. It's just that the function called to uppercase with not string doesn't even exist. So it's kind of a subtle but important distinction, and it will become important when we talk about overloading and things like that. But yeah, this is the most simple way, and you can obviously, if you have multiple arguments, you can apply that to all of them. Third argument, we can call it list and so on. I would say, well, this is probably a matter of preference, but um, even when my function works with multiple types of arguments, I like to um, I like to define the head that I'm expecting. And the reason for that is if you leave it as blank, which most functions you see are going to be left as blank, that means that the text argument could be any expression in Wolfram language or an expression that has any head in Wolfram language. And that makes your function more flexible, obviously, because, well, let's say this number argument, um, I can specify it to be an integer, but most likely my function will work even if the head is real. So if I specify one or the other, then my function is not going to work with the other one. So it's a trade-off. On the one hand, you make your function more restricted, but on the other hand, if the user passes something like something where it's not obvious that it doesn't work, um, then if your function allows any type of argument, then that argument will get passed to the right hand side, and if there's an error, you have to trace it back to the actual code on the right hand side. Whereas if you restrict the argument, you will just get this. You just get this syntax here saying basically that the function doesn't exist. So it's a trade-off. It is situational. It depends on your needs. So it is up to you to kind of decide to make that decision whether you want to be very restrictive in your arguments and catch errors early, or whether you want to be permissive and allow your functions to be more flexible. Okay, then another way to restrict our arguments is by including what we call a pattern test. So far we were talking about heads. Now we're talking about patterns, and patterns are a more flexible, a more extensible way of restricting your arguments. Although they could be simple, they could be. So as you can see here, let's look at the example actually, because this is also a good example. We're defining a function called redStyle that takes one argument called string. And the notation for a pattern test is this question mark, and then any piece of code that returns true or false. In this case, we have a string q, which will return true or false. And then on the right hand side, again, we have a simple code that takes the argument and it makes it red. So just to be clear, this function is the same as if we typed this. Only instead of restricting by head, we're including this pattern syntax here, and we're saying this argument must return true when it is passed to this function, otherwise it's not valid. But functionally, they are the same. So if you're doing something that is as simple as this, I would recommend filtering by head, just because it's easier to write, it's easier to read as well. But the real advantage of pattern test is that they can be as complicated as you want them to be. So here we have another function, which now in this case, you can see that our pattern test, here we're using a pure function inside a pattern test for a named function. So again, it increases the difficulty, it reduces the readability, I would say, but we can still read it. So we can see that what are we checking for? So we have a string argument and we're checking for something. So we're checking whether the argument is a string, first of all. So string q will return true for any string passed into it, and it will return false for anything else. Then we have the and operator here, which is denoted by this. And then we have another condition, which is string contains q. And this is where again our pure function comes into play. It checks whether whatever is passed into it contains go. In any case, in uppercase, lowercase, it doesn't matter. So this whole expression, if we look at the parentheses, this will only return true if both conditions are true. Um, if the argument is a string and if the string contains go. So let's look at how that works out in practice. So when we pass a piece of string, let's say text, let's go into the pattern test and see what this argument evaluates to in the pattern test. So if we insert text into string q, this is going to return true. So the first condition is met. However, the second condition checks whether that string contains go. And because text doesn't contain go, string contains q returns false. And because string contains q returns false, then the whole expression in the parentheses is not true. Therefore, this string is not valid. Therefore, the right-hand side of your function is not applied. And therefore, you get this, again, the undefined, this function doesn't exist of Wolfram language. That's a bit involved to explain. Hopefully, the example makes more sense than my explanation. It's a bit difficult to put it into words. But again, if you look at the second example, again, we have a string. And for this string, both conditions that we have here are met. Therefore, everything in the parentheses returns true. Therefore, the string is valid. Therefore, this is being applied to it. And we see the string with a green color. And again, if we pass something that is not a string, then it fails both conditions. Therefore, again, this doesn't exist. Um, Patterns can be assigned a label. I'm just a bit worried about time because I have a few other things to talk about. This is one of the challenges with these webinars where we have a lot of materials that I really want to cover all the basics, but then I find myself not having enough time. So I'll quickly talk through patterns and conditions, and then I'll move on to the next notebook. So patterns can be given a name by using this column notation. And this is essentially the same as doing this. But when you have multiple arguments, when you have a lot of arguments, you might find it more readable if you assign them a specific name. But functionally, they are the same. And again, here we're just checking whether something is a string. Not very interesting. Condition is probably the other kind of um, main way you can filter your arguments or you can restrict your arguments. And the way it works is actually very similar to a pattern test. And you can do this inside the square. Oh, so in terms of notation, use this slash semicolon notation. Now you can see when you have a lot of these shorthand notations, especially when you combine them into the same function, it greatly reduces the readability. So I'll say use them kind of advisedly. Um, and again, with conditions, it just checks whether it checks whether some condition is matched. So it's pretty self-explanatory. And here again, the example we have is functionally the same as having both style string string. So functionally, this is the same as this. It's just another way of accomplishing the same thing. Now, the value of using condition is that you can specify more complicated things, and I'm not sure if we have any here. Also, this is with the condition notation only, you can specify it after the square brackets. So you can see here we define a function, we have the argument in the square brackets, and then after that we have a condition which checks these arguments against some piece of code. This is only for condition. It doesn't work with head and pattern as far as I know. I just wonder if we have slightly more complicated examples with condition, and we do. So the main idea here is that again, situational application of condition is where you think that your code might be more readable by using that notation instead of restricting by patterns. Um, and in this case, you can see that you can essentially think of it, you have your function definition here, you have all of your arguments in square brackets and nothing else. And then after that, you have your filtering logic, so to speak. So that might make it more readable in some cases. It might not in other cases, but it's another one of those things where it's useful to keep them in mind, um, just in case you think you ever need them. I'm not going to go into too much details in these examples. Again, we're all of these, so heads, pattern tests, and conditions. They're all kind of accomplishing the same thing in that they're checking whether the arguments of the function that you have defined um, are what you expect them to be, essentially. Okay, let me see if there is anything more interesting in this notebook because I do want to get to the next one. Pattern sequences, not so much. Repeated, again, all of those things. I mean, this is where we get into less common syntax. So by all means, if you're interested, uh, you can look at them in your own time. But I'm not going to have time to go through every single one of those. Actually, optional. Okay, optional is the last thing that I'll cover in this notebook before I move on, because that is quite useful. And optional essentially allows us to specify what the argument should be if the user doesn't pass anything. So if we have a function that is that takes one argument, obviously when the user passes the argument, then we use the argument. No questions asked. It's fairly clear. But what do we do if the user calls the function but they don't pass any argument? In that case, we can define a default value which will be used if the argument is missing. Now, in some cases, you might want to provide a default value. In some cases, you might not. But in this case, we want to say that this function, um, if the user doesn't pass any argument to it, we will assume that the argument is this string called default text, and we'll evaluate the right-hand side with the default value. So you can see so we're calling the function twice. First time we're providing a string, then we get the expected result. But when we call the function without any arguments, then this default value is being inserted into the function, and we get our default text. So that's actually very useful for things like um, when you have arguments when you have a function that takes arguments, but in most cases the arguments have the same value, but you still want to maintain the flexibility of passing different values if you would like. But if in 90% of the cases this text function will have this value, you can just define it as default, and when you call it with that value, you don't have to pass in any arguments. But when you call it with a different value, if you want to call it with a different value, then you still have that flexibility. So that's one kind of more creative use of these optionals. Okay, next notebook. Not save that. So we'll be looking at notebook number 5 now, called useful tips. So if you are following along, you should have access to the whole archive, which gives you all of these notebooks. So just open notebook number 5. Yeah, let me just make that a bit bigger as well. And let's get into it. So we have covered pretty much all the basics that you would use when you're defining your own functions. You have named functions, you have pure functions, you have arguments, you have slots. Um, you know how to restrict arguments just to make sure that the arguments are always of the type that you expect them to be. You have optionals, so you pretty much have all the tools you need to kind of start writing your own functions that are going to be robust and readable and useful. So what I'm going to do for the next 10 to 15 minutes probably is just talk about some tips, some extra kind of things that you can keep in mind to make sure that your functions are the best versions that they can be. And then for the last 5 to 10 minutes, if you have any questions, feel free to drop them in the chat now, and I will do my best to answer them. But in terms of a plan for the rest of the session, I think I think we'll just have time to cover the useful tips. There are other notebooks, but it's very difficult to cover everything in 90 minutes. But let's see how we get on. Maybe we'll have time left for some other things. Okay, so in terms of useful tips, sorry, I clicked on this again. In terms of useful tips, we'll talk about variable localization, and that is very useful when you have kind of more complex functions that perform multiple operations on the same arguments. Typically, well, I'll talk more about it when we get there. Um, Adding syntax information to a function. So this is more about documenting your function, making sure that if somebody else is using it, they know what it does. Give a function special attributes. This is more of a, or at least I haven't used it a lot, so it was quite interesting to read about it. So I'll talk to you about it, and maybe you can find use cases for it. Speed and efficiency, quite important, especially if you're doing computation heavy workloads. Um, Progress monitor. This is more of a cosmetic thing you can add to your function. So if you have a function that takes a long time to execute, you might want to create a progress indicator, just so, even if it's just for yourself, just to see how it's getting on, making sure it's not frozen and things like that. But this is more of a kind of a cosmetic thing you can add to your functions. Extracting information from a function and common coding pitfalls. So these are the things that we'll try to cover. I would say that localization is probably the most important out of all of those things I listed. And the reason why it's the most important is that it really helps you when you're writing your own code. It really helps you because in an ideal world, your code always works the way you intend it to work, and there's no errors, there's no bugs, everything is smooth. But obviously, in practice, in real life, that's not always the case. And one of the most annoying experiences when you're programming is when you have a bug and you don't know where it comes from. And at least in some cases, the bugs that are difficult to locate come from scoping and from localization of your variables. So to put it very simply, if you have defined some variable here, let's say we have a variable called a, which has a value of 21, and then I have some function here, and I'm trying to do something. Let's call this argument a as well. I'm trying to do something here, and I have multiple expressions, and I do this. Uh, print a. This is just an example. It's a nonsense function. It doesn't do anything. Um, but what I want to, the argument that I'm trying to make is that if you have defined a, a variable elsewhere in your code, maybe earlier in the code, and you forgot about it, and you reference it later on, you might be expecting this a to refer to the argument of the function, but it's actually referring to the variable you defined earlier. So it's going to give you unexpected results, and you're going to be wondering, why is my code not doing what I expected to do? So when we talk about localization, is it's all about how to avoid errors like that. And we have a few very useful kind of built-in functions that help us with that. Um, and the main ones are with and module. And module is the one that I personally use the most. But let's start with because that has its uses as well. So with uses lexical scoping. So it replaces the variables with their assigned values immediately. So you can think of any variables you define inside with are treated like constants. So you're not able to change their values later on in your code. So you can see that here we define a to be 1, and then we try to assign a different value to a, and we get, in this case, actually a descriptive error message saying that you cannot assign, well, not very descriptive to be honest, cannot assign to raw object 1. Basically, it means that a is a constant. So um, the name of the variable is already replaced with the value. So this is the same as saying that 1 should be 2, which doesn't make any sense. So you get an error message. This is mainly useful for when you're trying to set up some initial data that you know is not going to change later on in your code. So that if you do try to change it later on in your code, you can get this message and you can immediately see where your error is. But just to give you a quick example with here we have a function, have our argument, and we have this with block where we define our initial data to be this random function. Then we can use it just as a either by itself or as an argument to other functions, but most importantly, we cannot change it. Um, so yeah, you most commonly use with when you're defining some. You can essentially, for all intents and purposes, you can think of variables defined inside with as constants and not actually as variables. It's probably the simplest way to think about them. But it ensures that you are not attempting to change something that should not be changed. And if you are attempting to change it, you get a very clear error message saying that you can do that. So the more useful function in terms of localization and scoping is module. And what module does is it defines local variables inside the function that are only understood to be valid inside the actual body of the function. So let me show you what I mean by that. So here we have with, as I mentioned, again, here we're using with to define our data, and our data is not going to change. So that's fairly clear. But we're also using module. And that's why I mentioned at the beginning that these localization functions are mainly useful when you're dealing with kind of a complex functions which involve multiple steps. So as you can see here, we have some helper functions, then we have our main functions. It's quite a substantial function. So when you have something that requires multiple steps, very often you save your intermediate results inside variables. And when you do that, when you have variables inside a function, that's when you're running into the risk um, of localization issues or of scoping issues. So what does module actually do? To get to the point, anything you define inside module is understood to be a variable that only applies inside the function. So here with module, we're saying that we have two variables, delete missing and select by age, and these two variables are only valid inside this function. So even if we have elsewhere in our notebook, let's say we have this variable and it refers to something, it will never get confused. So if you have module, it will never try to look up this definition that you have earlier in your notebook. It's only going to look inside the code. So it makes sure it makes sure that your functions are containerized, if you wanna think of it like that. Very, very useful for kind of avoiding scoping issue. And in terms of syntax, it's fairly simple as well. So it takes a list of the functions that you want to be local, and then the second argument is the actual function. And when you use those variables, you can have the peace of mind that you're never going to run into um, scoping issues. So that's probably the most, I would say, probably the most useful function in this notebook. Again, it's a function that you'll find yourself using a lot, and it's a function that when you're reading other people's code, you'll find that they have used a lot as well. Um, Another way to think about localization is with block. Um, a bit less common than with an module, but useful as well. So block uses dynamic scoping. So it sets up uh, well, the explanation here, it sets up a miniature global environment in which the values of the symbol can be temporarily reassigned. Um, it's useful for reassigning built-in constants. So this is where, when we're talking about environmental variables, you have um, a lot of environmental variables that are derived from your system, from your operating system, from your environment, whatever. So in some cases, it might be useful to change those temporarily. Now, obviously, you don't want, or in some cases, you can't change the system-wide variable. So you can wrap it inside block, and then you can, um, uh, if you want to think of it in the way of creating a mini virtual environment in which the global variable is redefined to something else. So in this case, we have block, and we are changing the time zone, which time zone is something different. So in my case, it is 1 because I'm in the UK. But let's say I'm testing something with a different location and I want to change that. Now I could go into my computer settings and change my clock and my time zone, but ideally I don't want to do that. So a much more simple and a much more robust way is to kind of change it inside block, and then this environmental variable only applies to the code inside block. And you can see that we can give it any value we want, well, any valid time zone value we want, and then we get a different time without having to mess around with our system settings. Again, a bit more niche, but might be useful if you're dealing with a lot of environmental variables. Um, Here we have another example. So I'm just reading the code to see what it does. Um, Makes an engineering estimation for the volume of planetary body by assuming that pi is 3. Oh, okay. So obviously, pi always has its own value, but if you want to define it to be something else, you can do that inside of block as well, and you can see how that impacts your calculations. Dynamic module. So this is something where a lot of functions in Wolfram language always already use by default. So it is unlike, also, yeah, this is a good example. So it is what manipulate uses behind the scene to ensure correct scoping. So it's it's very unlikely that you need to use this in your code. So probably not go into too much detail into it, but this is especially when you're developing things like user interfaces and these, for example, these sliders and any kind of interactive elements, and you want to ensure proper scoping, um, dynamic module is your go-to function for that. Not going into too much detail. But when you use manipulate, kind of under the hood, it already does the proper scoping for you. So to make sure everything works. Um, Automatic localization, as I was just touching upon, actually, a lot of the built-in functions in Wolfram language already use proper scoping kind of under the hood to make sure that everything is properly scoped. Um, so yeah, there's nothing you really need to do inside that. But again, just to be kind of a bit more explicit about what is happening here. So here we're using, let's say, table, for example, and we have this x variable where x goes from 1 to 10. Again, table uses very strict scoping. So even if I have something here previously in my notebook, let's say x is 491, when I pass x inside table, it knows not to look outside its scope. So we always get the same result regardless of whether the name of the symbol we use inside table is previously defined or not. So these are just things that happen automatically and you don't need to worry about them. But if you're building your own functions, it's important to kind of note that table is a very basic kind of iterator function. So I guess it's important to know that it already does its own scoping, so you don't need to wrap it in things like width or module or anything like that. It is going to behave as you expect it to behave. Um, a few other things. So now we're getting more into kind of error handling and more descriptive error messages. So this is where we have throw, catch, confirming, close, quiet check. They all do all of these functions that you see listed here all do pretty similar things with some slight differences. Um, Again, if you're writing substantial functions, it is worth looking into them. And that's mostly to kind of improve user experience. Mainly so that when if a user is using your function and they're doing something wrong, you can actually tell them, hey, this is what you did wrong, rather than throw some vague error message and let them figure it out for themselves. Syntax information, again, this is more concerned with documentation. Um, so if you're using Wolfram language from within Mathematica, you have a lot of kind of syntax highlighting features enabled by default. And this is where I use something like even Q, for example. I don't pass any arguments. You can see this red arrow here indicating that it is expecting an argument in that place. So you can do that with your own kind of custom defined functions as well. And the way you do it is you use this kind of syntax information super function, so to speak, and you can specify a lot of things just so you can use the syntax highlighting features that already exist in Mathematica for your own functions as well. And just to show you what we're doing here, we're saying that for the function f, we are expecting that the arguments will look like this, and this is a one blank. So we're saying that there's going to be one argument of any type. So you can see that if we try to define f without any arguments, we get the helpful syntax highlighting arrow. If we try to define f with more than one argument, we have the second argument and the comma highlighted in red saying this doesn't belong here and things like that. Other syntax information as well, but it's mainly kind of following the same idea. Let me see. There was something more interesting in this notebook just to finish with. I'll probably finish with speed and efficiency because it's quite important. I mean, Wolfram language is known for its speed and efficiency, especially for an interpreted language. So a lot of people use it for kind of computation-heavy workloads. So speed and efficiency are considerations that users care about. So let's say a few words about them. Let me give you some tips about how to maximize the speed of your functions with very basic kind of steps. The first tip is use decimals. So essentially use real numbers instead of integers because computations on real numbers are more efficient than those on integers. So you can see here we have two lines of the same code, and in one case we use one, which is an integer, and we can check this by passing it into the head function. And if we use one decimal, that's a real number. So even though both of those expressions refer to the number one, they have different types or different heads in Wolfram language terms, and that can affect how efficiently they are being computed upon by your CPU. So you can see that even though the rest of the code is the same, this line takes much longer to execute than this line, where the only difference is we added a decimal here. So if you can do computation on real numbers rather than integers, um, here are some more examples um, with using the decimal notation, which I don't see what is being used, what is different in this case, but it is basically driving the same point. Oh, this is for some specific functions. Expect things to be real or integers, for example, solve. So another tip is to use compiled functions. So as I kind of mentioned a few minutes ago, Wolfram language is typically an interpreted language, meaning that any code you write gets passed to the Wolfram language interpreter, which then converts it to machine instructions, and then it's being passed to your CPU. And that's very common. A lot of languages are interpreted languages, at least to some extent. Even if you think about more common languages like Python, Ruby, and things like that, JavaScript, they're all interpreted languages, but they all have some compiled features to them. And in terms of Wolfram language, we have this compile function, which there are a lot of caveats. You cannot really apply to every single thing, but there are things you could apply to. And actually, one of my colleagues here at the UK office is writing a webinar about the Wolfram language compiler, so he would be able to give you a lot more information. He used to work on the compiler quite a lot. So but the main idea behind using the Wolfram compiler and the reason why it exists is so that if you have a function where you want to squeeze out the maximum possible speed out of it, you really want it to be a compiled function rather than an interpreted function. And this is what the compile function is intended to do. Again, as I mentioned, with a lot of caveats, but if you can compile your function, that is something that will speed it up significantly, because then it's converted to machine instructions directly, and then you can use the full features of your CPU. You don't need to go through the interpreter, so you have nothing slowing you down. Let's see how the compiled function compares to the normal one. Again, here we have, sorry, I should have said, we are defining two functions which are identical, except that the second one uses compile and the first one doesn't. And we can see that the compiled function is about 3 times faster for doing the same thing um, than the normal one, so to speak, the interpreted one. And obviously here the differences are not that big. So we have 1.2 seconds and 0.04 seconds. But if you have a function that takes 10 hours, which let's say you have some machine learning workflow and you have millions of rows in a database that you're feeding it into, that can easily take hours. And well, I think compile is not going to work for that specific example, but you kind of get the idea that for things that are computation heavy, compile is going to help a lot. And probably the last thing I'll mention is that I kind of touched on that at the beginning of the webinar, but we have a lot of built-in functions that are designed to be efficient. So there's a lot of effort that goes into making sure that those functions are as efficient as possible. So if you're trying to do something and there is a built-in function, even if it's a simple one, it's probably worth using that instead of writing your own. One, it's more simple, so you don't need to write it from scratch. But two, it's usually more efficient. It's quicker. And here again, there are some examples that will kind of show you that. So if you use map, and then if you just use flatten directly. I think I'll leave it at that probably. We have using an IDE. If you're dealing with a project with a lot of files, you can use external IDEs. So for example, I think this one is IntelliJ IDEA. A lot of IDEs, VS Code, IntelliJ IDEA, some other ones probably that. Oh yeah, Eclipse. A lot of those have Wolfram Language plugins where you can get all the nice syntax highlighting and things like that. So that's another thing that can kind of, it obviously doesn't speed up your functions, but it might speed up the rate at which you write Wolfram language code if you're more familiar with some IDE and so on. But here we're already getting into kind of more minor things. So I think I'll just leave it at that. If you have any questions, feel free to put them in the chat. I have a few minutes to answer them. And if not, thank you for listening. And hopefully that was interesting to you. Hopefully you got something out of it. It is a fairly basic one, but it's nice to kind of do a quick recap, even if you're familiar with most of the things that we were talking about. Alex Osman is saying, thank you. I'll try to use these tools and promote the Wolfram way. I'm learning to vibe code at the moment. That's awesome, Alex. Keep at it. Hopefully this was useful to you.